Morning, measure theory. In that, we will start with the integration. In that integration, we will concentrate only on the Lebesgue integral. These things we already discussed. Introduction, shortcoming of Riemann integral, pictorial representation with an example, the Lebesgue integral of bounded function over a set of finite measure, theorems related to simple function. In this class, we will discuss mainly on problem solving hour. In today's class, we will concentrating on Lebesgue monotone convergence theorem problem related to that. Sometimes it is mentioned that it is Beppe-Lewis theorem. Using Beppe-Lewis theorem, you can verify some of the problems are given. This is the one of the problem related to that. If -1 less than a less than 0 and f is a mapping from closed interval 0, 1 to r, we define as f of x is equal to set of all x power a. It is ranging from 0 to 1. If x is equal to 0, it is 0. Means monotone convergence theorem. How to verify this one means, first, suppose sometimes evaluate means one part you can do it, then it become get the solution for the Lebesgue integration. Suppose you can verify means two ways you must be verify for this one. For each n, we define a fn mapping from 0, 1 to r, the interval, given interval. Fn x means f of x become fn x, x power a 1 by n less than or equal to x less than or equal to 1, 0 less than or equal to x less than or equal to 1 by n. Here, maybe you know that here we observe that f of x is fn is a increasing sequence because it's monotonic increasing function, therefore such that fn is converges to f. And also you can find the integral upon 0 to 1 fn x into dx. Here the interval is ranges from 1 by n less than equal to x less than or equal to 1. Means here the 1 by n to 1 x power a dx plus here 0 to 1 by n become 0. Then this become, if you integrate, this is x power n formula. If x power n can be integrated means that is x power n plus 1 divided by n plus 1. Means here x power n plus 1 means x power a plus 1 divided by a plus 1. Then apply in place of x. In place of x here, you can make that as a 1 by n. If you're substituting here, 1 by a plus 1 is a constant, 1 minus 1 by n. 1 by n to the power of a plus 1. Then if you take, because the Beppe-Lewis theorem, we can say that limit n tending to infinity, integral upon 0 to 1 fn x dx. Means here this is 1 by infinity become 0, then you get 1 by a plus 1. Next, the converse part, it is equal to, by monotone convergence theorem, integral upon 0 to 1 f of x dx exist. F of x dx is exist means you know that here x power a. Integral upon 1 by 0 to 1 power here directly 0 to 1 x power a. X power a is exactly similar way here, x power a plus 1 divided by a plus 1. If you put x is equal to 1, you get same thing, 1 by a plus 1 for the left hand side function. Then both are one and the same, therefore Beppe-Lewis theorem is verified. Similarly, one more problem, show that the theorem, bounded convergence theorem, is applicable to this problem. Means you know that bounded convergence theorem, mod fn is less than or equal to some capital M. M is a bounded, means mod if n is less than capital M. You can make that function into a bounded to some particular value. Here, the given problem is fnx is equal to nx divided by 1 plus n square x square. Take here n square x square as a common factor for here in the denominator, highest power. Then this become what happens 1 by nx plus here also nx. Then we can make this in a root, the completing the square form, that is a plus b is there. This can be written as 1 by root of nx. Root of nx means that is 1 by root nx minus root of nx the whole square plus 2. You know that a plus b is there, means a plus b, that is a square plus b square can be written as a minus b whole square plus 2. That is the formula. You aware of that, you have studied in your high school itself. Using this concept here, we can make this 1 by nx plus nx can be written as 1 by root nx minus root nx the whole square plus 2. Here, definitely this must be bounded to less than or equal to 1 by 2. Means here we take an m is equal to half, then this given function mod fnx is bounded to less than or equal to m. Means if it is bounded to some positive number m, means we can apply a Lebesgue convergence theorem. What happens the Lebesgue convergence theorem? In the left hand side of this Lebesgue convergence theorem, limit of n tending to infinity integral upon 0 to 1 nx divided by 1 plus n square x square dx means, if you observe this integral, this is 1 by x dx form. Here x, if you take 1 plus n square plus x square, here you know that 1 by 1 plus x square, or we can write this is the whole square is equal to t here. Then what happens here, if you differentiate this, this become 2 times nt nx into 1 into dx is equal to dt. Is it correct? You studied in your PU class itself. Here, then this become 1 by t. Then what is the derivative here? 2 is not present. That's why we return 1 by 2. 1 by 2 into here 1 by 2. N square is a constant actually. 1 by n square, another n will be coming here. That is 2n square will be there. That's why here mentioned 1 by 2n. 2n into log of 1 plus n, because 1 by t means log t. Log t means log of 1 plus n square plus x square. If you applying the limit, this become infinity by infinity form. Infinity by infinity or 0 by 0 form means we can apply a L'Hospital rule in the differentiation concept, limit and differentiation concept. Then we differentiate the numerator as well as differentiate the denominator also. Then this become 1 by 1 plus n square x square plus 2n x square. Then denominator become 2 into 1. Then whole thing will becoming denominator. If you take n as a common, here also n as a common, n square, then 1 by n will be there. If you are applying n tending to infinity, the function, the value become 0. 1 by infinity is equal to 0 here. Similarly, right hand side of 1, we can change the integral with respect to limit 0 to 1, limit of n tending to infinity, nx divided by 1 plus x square. If you take n square as a common, then here 1 by infinity form. If you are applying n into 0 into dx, that becomes 0 means left hand side is equal to right hand side, means it verifies the Lebesgue bounded convergence theorem. This is the two examples I given. Now we move on to now we will move some more problems. Show that if f is a non-negative measurable function, then f is equal to 0 almost everywhere if and only if integral upon f into dx is equal to 0. Here what is given? The given function is a non-negative measurable function. Then if there are two parts, f is equal to 0 almost everywhere if and only if the integral upon f into dx is equal to 0. First, we will start with the first part. What is given? F is equal to 0 almost everywhere, and it is an integrable function, means there is a simple function phi is a some single function will be present, and also that related to f, phi is less than or equal to f, then clearly integral upon phi into dx is equal to 0. You know that how it is 0 means integral upon f into dx means supremum of integral upon phi dx. Phi is less than or equal to f, and also f is a non-negative function. It starts from 0 onwards, then definitely this function become 0, means integral upon f dx is also 0 here. Now what is converse? Integral upon f into dx is equal to 0, and it is a measurable function, then definitely there is a set relationship also there. Then En can be written as set of all x such that f of x is greater than or equal to 1 by n, means then definitely integral upon f of x dx can be written as greater than or equal to integral upon 1 by n chi en, because chi en is a characteristic function with respect to the set function en. Then you know that if you make this 1 by n is a constant, we can take outside, then this becomes measure of that set. Measure of en is a singleton, it is 0, therefore the value become 0. Product is also singleton set, it become 0 here. But set of all x such that f of x greater than 0 means each function can be written in terms of union of disjoint sets, that is union of n running from 1 to infinity en here f. So definitely f is equal to 0 almost everywhere. Next, one more example. If f of x 0 to 1 defined as f of x is equal to 0 if x is rational, if it is n, x is irrational. Here we have taken as n is the number of zeros immediately after the decimal point, means you can choose decimal point, means it is up to 10. 10 means it is 9 is the double digit, you know that. Decimal points will be arise from 0 immediately. Representation of x on the decimal scale show that f is measurable, and also evaluate 0 to 1 f dx. Here what is given? The function x lying from 0 to 1, and we choose g of x is equal to n. It is lying between 1 by 10 power n to 1 by 10 power n plus 1. Here minus sign will be there. Then n is running from 0, 1 to etc. And g of 1, that particular point value is equal to 0. And also f is less than or equal to g, because we are chosen, because always measurable function can be comparable. That's why we make f is less than or equal to g, means f is equal to g is almost everywhere. Similar to above problem, we can say that using this means f is equal to g almost everywhere means definitely f is also measurable here. Then the integration part. Integral upon 0 to 1 f dx means integral upon 0 to 1 g of dx. Here summation n0 to infinity n times the interval is 1 by 10 power n minus 1 by 10 power n plus 1. Here we make that function, it is equal to here n, but it is in the range. Means that is 1 by 10 power n minus 1 by 10 power n plus 1. You know that 10, we can write directly also if you aware of that. Take a LCM of this means 10 power n is a common, then remaining is here 1 minus 1 by 10, that is 10 minus 1 is 9, 9 by 10 power n plus 1. You get this one. How to solve this one means we can solve directly. You can take it this function as yes here, apply n running from 1 to infinity means 9 taken common, 1 by 10 square, 1 by 2 by 10 cube, 3 by 10 power 4, etc. Here we take 1 by 10, multiply throughout by 1 by 10, both the sides, then this becomes 1 by s by 10, 9, 1 by 10 cube, 2 by 10 power 4, etc. Then you can subtract from this to this, means 9 is a common, both you can take common. 1 by 10 square minus 1 by 10 cube means what happens here? That is 1 by 10 square will be remains 1 by 10 square, 1 minus, that is 2 minus 1, you get 1, 1 by 10 cube, 1 by 10 power 4, etc. will be remains here, 2 minus 1, 3 minus 2, etc. Are you understand here? 2 minus 1, 3 minus 2, 4 minus. In this way, you get 1 by 10 square, this one, 1 by 10 cube, 1 by 10 power 4, etc. Means it is a geometric series. You know that geometric series infinity means a by 1 minus r. Here, a is 1 by 10 square. Here, the ratio is equal to 1 by 10. Then 1 by 10 squared divided by 1 minus r means 1 by 10. If you simplify this, you get 9 into 1 by 100 into 10 by 9. If you here rearranging this, you get s is equal to 1 by 9. Is any doubt?
No, sir.
Okay. Now, exactly similar way, you can do it yourself. Prove that f of x is equal to 0 at every point of the Cantor's ternary set. Exactly same above problem and say this one is same, but dimension in the name Cantor's ternary set, and f of x is equal to p in each of the complementary interval of the length 3 power minus p. Then integral upon 0 to 1 f of x dx exists in the Lebesgue sense. Here it is given 0 for all x belongs to E and by contour ternary set, and p on the interval 1 by 3 power p. Here 0 to 1 f of x dx is equal to here summation p running from 1 to infinity p times 2 power p minus 1 divided by 3 power p. If you're rearranging this, you get this one. Then simplify. This is the hint I given. You get a solution is 3. And work it out. Now I will move on to one more example. Give an example which yields a strict inequality in fatous lemma. Consider fn r to r such that fnx is equal to 2 for n less than or equal to x less than or equal to n plus 1, because it is monotonicity will be there, then 0 otherwise. Then if you take limit n tending to infinity, fnx is equal to 0, therefore integral upon f over r is also 0. Here the interval is taken, that is n to n plus 1 be taken as that is the E set, measurable set, then fnx is equal to 2 on E, and the complement fn of x means this is the one, then definitely other one is the complement fnx is equal to 0 on E dash. Then integral upon r fnx dx is equal to, we can write the set and its complement, sum of that, only you get a value. Integral upon E fnx dx, integral upon fnx dx E dash, here it is n to n plus 1. The fnx value is 2 into dx plus fnx, here E dash means that is 0. Then 2 into 1, 2 into dx, x will be there, n plus 1 minus n become cancelled, you get only 2. Means here the value, the integral upon f over r is equal to 0, but here integral upon fnx of r with limit n tending to infinity, the value is 2, then 2 is greater than 0, means integral upon f over r is less than the limit of n tending to infinity integral upon fn, means this satisfies the strict inequality for fatous lemma. Now we move on to one more problem. Show that integral upon 1 to infinity dx by x is equal to infinity. This one you studied in your complex analysis in the contour integration as well as the general form of infinite series. You know that 1 by x is continuous for x is greater than 0. It is measurable. Hence, if it is a measurable, then definitely it is integrable also. Integral upon 1 to infinity x power minus 1 by x can be written as x power minus 1 dx is greater than integral upon 1 to n x power minus 1 dx. Then this can be written as limit of n tending to infinity integral upon 1 to n x power minus 1 into dx. Now we note that 1 comma n, that is an interval, because instead of infinity we make it as 1 comma n, union of all the intervals n p running from 2 to n, p minus 1 comma p. You know that 1 by x is greater than 1 by p, then that is lying between p minus 1 to p. Then this can be written as integral upon 1 to n 1 by x dx is greater than the sum of p running from 2 to n 1 to p 1 by p with respect to simple function phi of an interval p minus 1 to p dx. Then this become 1 here, then you get only 1 by p. You know that 1 by p, it starts from 2, means 1 by 2 plus 1 by 3 plus 1 by 4. It is a divergent series. Divergent series means the value of the sum of the value become the divergent series value is equal to infinity. Integral. Then definitely integral upon 0 to 1, 1 by x dx is equal to infinity. Means this is the one of the problem you must remember.